Okay. Or this lesson, in fact. So starting with the moment of inertia for a rod rotated around an axis through one end. So if we have a rod and it has some length L, it gives us that the moment of inertia about this axis is ml squared over 3. And it wants us to prove that the moment of inertia rotating through its center and perpendicular to its length is ml squared over 12. So we can just do the same trick as I have in a previous lesson and use that I is the integral of r squared dm and then start summing up masses. We can also use a kind of nifty little trick here. So armed with the moment of inertia about its center of mass, so that would be the middle, we can find the moment of inertia about any other axis system by just adding md squared, where d here is whatever distance we're moving in. So in this case, our d would be L over 2. Now we're given the moment of inertia about this axis and asked to find the moment of inertia about its center of mass. So we would rearrange this. So our center of mass inertia would then be the I we're given minus md squared. So the moment of inertia we're given is ml squared over 3 minus m, and that's L over 2 squared, which is ml squared over 3 minus ml squared over 4, just expanding the square. Now we need to give these this same denominator, so we need to multiply this by 4 and multiply this, or 4 over 4 I should say, and then multiply this by 3 over 3. And so then this is 4 ml squared over 12 minus 3 ml squared over 12, which is equal to ml squared over 12. And so the moment of inertia about its center of mass is ml squared over 12, which is what it asked us to show. So that looks good. So again, just to reiterate this this equation here, that means that if you have the moment of inertia about an axis which passes through its center of mass, you can find the moment of inertia about any axis which is parallel to that by just adding md squared. So you can easily translate any moment of inertia with that equation. Okay. So the solution here does the normal thing and sums up little dm's, so that's handy as well. So we can define our dm and go through and find the moment of inertia as the integral of dm r squared, and then with their definition, they get the moment of inertia for the rod from one end is ml squared over 3, which was given in the question. And then for an axis which passes through its center, then we're going to just integrate from minus L over 2 to L over 2, which gives us our ml squared over 12. So the solution is correct. but is solvable with the equation I gave here. Okay.